You think black holes are just really dense stars that collapsed? Heavy things that pull everything in? Fine. But why can't light escape? Light has no mass. Gravity pulls on mass. So why does gravity affect light? Most people have never really thought about this. They just accept it. Black holes are so strong even light can't escape. That's just how it is. But that's not an answer. That's just repeating words. When you really ask why light can't escape a black hole, when you dig into what's actually stopping it, you discover something so strange, so fundamentally different from everyday gravity that it changes everything you think you know about space and time. Black holes don't pull light in. They bend space itself so severely that there's literally nowhere else for light to go. Let me show you what I mean. Let's start with something simple, something everyone knows. Things fall. Drop something, it falls down. Newton said gravity is a force. Mass attracts mass. The earth pulls you down. You pull the earth up, but you're lighter, so you move more. Simple. Makes sense. For Urbeck years, this worked perfectly, predicting planetary orbits, explaining tides, calculating trajectories. Newton's gravity was the law. Then Einstein came along. And he asked a strange question. How does gravity work so fast? And the sun is just or 10 million miles away. If the sun suddenly disappeared, Newton's law says Earth would immediately fly off in a straight line. Immediately. But wait, how does the Earth know the sun disappeared? Information can't travel faster than light. Nothing can. So there should be a delay, about Bott minutes, the time it takes light to travel from the sun to Earth. But Newton's law has no delay. Gravity just acts instantly across empty space. Einstein didn't like this. He didn't like action at a distance. He didn't like instant effects. So he thought about it differently. Change it. What if gravity isn't a force at all? What if massive objects don't pull on other objects? What if they bend space itself? Imagine space as a trampoline. Flat, smooth. Now put a heavy ball in the middle. The trampoline surface curves down around the ball. Now roll a marble across. It doesn't go straight. It curves toward the ball. Not because the ball is pulling it, because the surface itself is curved. The marble is just following the straightest path it can on a curved surface. That's gravity. Mass curves space. Objects move along the curves. Einstein worked this out mathematically. He called it general relativity. And he made predictions. Light passing near the sun should bend. Not because the sun pulls on it, because space near the sun is curved. Light follows the curve. In Chen-Joule by Joule, during a solar eclipse, astronomers measured starlight passing near the sun. It bent, exactly as Einstein predicted. The amount of bending matched his equations perfectly. Space is curved by mass. This was huge. This wasn't just philosophy. This was measurable, testable, real. Now, here's where black holes come in. If a little bit of mass curves space a little bit, what happens if you put a lot of mass in a very small space? A star, for example, is big. The sun is Bopite Loser Ling miles across. Huge. The curvature of space around it is gentle. Light bends a little, not much. But what if you compress the sun, squeezed it down? Same mass, smaller size. The curvature gets steeper, squeezed more. Steeper still. Now, normal stars don't collapse because they're hot inside. The heat creates pressure. Pressure pushes out. Gravity pulls in. They balance. But when a massive star runs out of fuel, the pressure drops. Gravity wins. The star collapses. And if the star is heavy enough, nothing can stop it. Not atomic forces. Not nuclear forces. Nothing. It collapses all the way down to a point. Well, effectively a point. We call it a singularity. All the mass compressed into an infinitely small space. And around that singularity, space is curved so severely that something incredible happens. There's a boundary. We call it the event horizon. Outside this boundary, you can still escape if you go fast enough. Light can escape. Inside this boundary, space is curved so much that every direction you can move, every possible path forward in time, leads toward the singularity. Not because something is pulling you, because the geometry of space itself gives you no other option. It's like being on a waterfall. Once you go over the edge, every direction you can swim, even straight up, still leads down. The water itself is falling. You're just moving with it. That's what happens inside a black hole. Space itself is falling into the singularity. Faster than light. Light tries to go outward, but the space it's in is falling inward faster. So the light gets carried in. It's not that light isn't fast enough to escape. It's that there is no outward. Every direction is inward. Let me say that again. Inside the event horizon, the future direction of time points toward the singularity. Just like outside a black hole, the future direction of time points forward into the next moment. Inside, the future points inward. You can no more avoid falling into the singularity than you can avoid moving into the next second. It's not a place you can escape from. It's a time you cannot avoid. Danger. Now you might ask, but what about going really fast? What if you had a super powerful rocket? Doesn't matter. Speed doesn't help because you're not fighting against a force. You're fighting against the geometry of space-time itself. It's like asking, can you go fast enough to travel backward in time? No, because that's not how time works. Same thing here. You can't go fast enough to escape because escape isn't a direction that exists anymore. And here's another way to think about it. Light always travels at the speed of light. Always. Through space. But space itself can move. Space can expand. Space can contract. Space can fall. And inside a black hole, space is falling into the singularity faster than light. So even though light is moving at maximum speed through space, the space itself is falling faster, carrying the light inward. The light never slows down. It's always going at light speed. But it still gets pulled in because the thing it's moving through is falling faster. And here's the beautiful part. This isn't just theoretical. We've seen it. We've measured it in Arsène Ling-Isserjo. The Event Horizon Telescope took a picture of a black hole, the supermassive black hole at the center of the galaxy M Bachelor T. You can see the event horizon. You can see the shadow. Light from behind the black hole gets bent around it. Some light escapes, curves around, reaches us. We see a ring, the photon sphere. But light emitted just a little closer inside the event horizon never escapes. It's gone. Captured not by force but by geometry, we've also detected gravitational waves. When two black holes merge, they create ripples in space-time itself. We detected those ripples. We measured them. The frequency, the amplitude, everything matched Einstein's predictions exactly. Black holes exist, they merge, they warp space-time. This is real, this is measured. And here's something even stranger. If you watch someone fall into a black hole, you'd never see them cross the event horizon. From your perspective, far away, time near the event horizon slows down severely. As they get closer, they move slower and slower and slower, asymptotically approaching the horizon but never quite reaching it. Their image gets redder and dimmer as light struggles to escape the intense curvature, but you never see them go in. From their perspective, though, they fall right through. No barrier, no wall. They cross the event horizon in finite time. And once inside, they have maybe seconds, maybe less, before they hit the singularity. Two different perspectives, both correct. Time is relative. Now let's go back to Newton for a moment. Newton's law of gravity worked for Urbach years. It still works for most things. Sending rockets to the moon, calculating planetary orbits, understanding tides. For weak gravity and slow speeds, Newton's law is accurate enough. But for strong gravity, for high speeds, for extreme conditions, you need Einstein. You need general relativity. And black holes are the ultimate extreme condition. The place where Einstein's equations matter most, but here's the thing, even Einstein's equations break down at the singularity. Inside a black hole, at the very center, our equations give infinities, infinite curvature, infinite density. That's a sign that we don't fully understand what's happening there. We need a theory of quantum gravity, a theory that combines general relativity with quantum mechanics. We don't have that yet, not completely. People are working on it. String theory, loop quantum gravity, other approaches. But we're not there yet. The singularity is still a mystery, and that's okay. That's how science works. You push the boundaries, you find the limits of your theories, you discover new mysteries. Each answer opens up new questions. Newton explained falling objects and planetary orbits. Einstein explained Mercury's orbit and the bending of light. We've explained black holes and gravitational waves. But there's more, always more. Dark matter, dark energy, the Big Bang, quantum mechanics. Each discovery is a tool for the next discovery. The avalanche that started 7 years ago is still going. We're still avalanching along at high speed at this time. So why can't light escape a black hole? Because inside the event horizon, space is curved so severely that every possible path, every direction you can move forward in time, leads to the singularity. Light doesn't slow down. Light doesn't get pulled. Light just follows the geometry of space-time. And that geometry gives it no choice. The black hole doesn't trap light with force. It traps light with curvature. It bends space itself into a shape where escape is not a direction that exists. That's not weakness, that's geometry. And the fact that we can understand this, that we can predict it, measure it, photograph it, that's the beauty of physics. Not comfort, not simplicity. Truth